Welcome, ladies and gentlemen, to this talk about representative structure elements for the fatigue assessment of additively manufactured components. My name is Matthias Hell from the Fraunhofer Institute for Structural Durability and System Reliability, LBF, in Darmstadt, Germany. I'm talking to you today on behalf of my colleague Rainer Wagener and also on behalf of my colleague Andrea Chiocca, who is working for the Department of Civil and Industrial Engineering for the University of Pisa. Keeping in mind that there is a large variety of different influencing factors which differ from classical or state-of-the-art manufacturing processes, it's worthwhile to take a moment and recapitalize what are the requirements on an industrial design concept for additively manufactured components. First of all, we have to define dedicated material properties. Due to the nature of the manufacturing process, these will differ by large from the material properties for classical manufacturing processes. The second one is the transferability. That means how can we transfer the material properties which will be normally derived by specimen testing to the component geometry. Then another point is considering the main influences on the fatigue life. For example, the component geometry, the loading case, and the next step is how can we reliably assess different loading conditions and different component structures. And the last but not least, especially for an industrial design concept, we have to make sure that there's an improved ratio of computational effort and simulation accuracy, which will then enable the lightweight potential and get a benefit of design freedom for additive manufactured components. The specific features of the material behavior of additively manufactured specimens will be treated differently regarding to the fatigue concept that has been chosen for the fatigue assessment. We can differentiate two types of fatigue concepts. One are the load-based concepts, which are based on a linear elastic stress-strain behavior. They normally assume homogeneous property distributions, and they have sensitivity factors to shift the SN curve, for example, the notch sensitivity factor. Then there are strain-based concepts, which feature an elastic plastic stress-strain behavior. They're describing the local material behavior of an infinitesimal small volume in a very classical formulation. And the pore geometry and population would have to be included into the FE model, which is rather cumbersome and entails a large numerical effort. In order to be able to estimate the fatigue life of a component, we need a fatigue life curve, which has to be derived experimentally, and it will be derived strain controlled in the low cycle fatigue regime and stress controlled in the high cycle fatigue regime and the very high cycle fatigue regime, in order to be able to increase the test frequency to a practical value. As you can see here in the low cycle fatigue regime, it's according to the strain life curve, it's composed of a plastic and elastic part, and in the high cycle fatigue regime, it contains the results of the stress control tests, which are linear elastic. Please consider these three cross sections all made of the same material. Even if we would put them all to a single stress value, they will have different fatigue lives, referring to the composition of the boundary layer compared to the bulk material, and also referring to the defect density that you can observe. Of course, all relevant influencing factors will superimpose each other. Nevertheless, it is necessary that that one tries to abstract single influencing factors by fatigue testing. So what you can see here On the left side is the influence of the build direction. There were two build directions investigated. One is perpendicular and one is parallel. And you can see that there is a significant difference between both. The defect mechanisms, the build direction, and other influences lead to a quite different view on the notch behavior, which differs largely from the notch behavior for classically manufactured materials. If you direct your eyes to the right side of this slide, you will see the results of fatigue tests for differently notched specimens. We have a KT of 1.0, 1.7 and 2.3, and you can see here the results for the 1.0, the unnotched specimen, and the slightly notched specimen with a KT of 1.7 nearly coincide. The curve and the results for the KT 2.3 lie significantly beyond those two. One of the factors influencing the notch behavior may be the pore population, which itself depends on the exposure strategy. On the left-hand side, you see a schematic representation of the pore population depending on the build direction and also whether it is on the upskin or the downskin side. On the right-hand side, you see a finite element simulation of a smooth surface of additively manufactured specimen, and on the other side you see the very rough surface. On the smooth side you have a well-contained, highly stressed volume with around about 0.2 cubic millimeters of content, and on the rough side for the same geometry this highly stressed volume is reduced to 0.12 cubic millimeters. In additively manufactured components, we usually have those different types of materials coming together in just one component. We have sound material as well as very porous material and intermediate states. Representative structure elements now yield a method to treat all those differently shaped or differently configured materials with one single approach. So we can distinguish three types of structural elements. The first one is the sound material. The second one is sound material combined with single imperfections, like for example surface roughness or single defects. And the third one is the one who combines the first and the second order representative structural elements to global elements which exhibit behavior that is combined of the of the sound material and the defected material. This slide contains the fatigue life curve and the stress strain curve for a titanium aluminide. On the left hand side you can see the fatigue life curve. Please mark here the different control methods that were used. For the low cycle fatigue regime, the experiments were strain controlled, and for the high cycle fatigue regime, the experiments were stress controlled. You can see here the curves for the specimens having two different thicknesses, T equals 1.0 and T equals 2.3, nearly coincide. For the stress strain curve, we can clearly see a difference. The thicker specimen with a thickness of 2.3 millimeters has a Young's modulus of 100 gigapascals, and the thinner specimen has a Young's modulus of only 95 gigapascals. This slide presents a comparison between the well-known technique of submodeling within the finite element simulation and the way the representative structure elements of different orders work. For the submodeling, we usually start with a very coarse meshing, and we transmit the boundary conditions to detailed submodels with a finer mesh until we get a solution for our problem with sufficient accuracy. For the represent structure elements, we start with a sound element, which would be the representative structure element of first order, and then we combine these elements into representative structure elements of second order, containing also imperfections, and the last step would be combining those RSEs of second order into representative structure elements of third order, which also contains surface imperfection as well as the component geometry. In order to understand how the pores work and how the interaction between the pores affects the material behavior, we need numerical support to derive a representative structure element. You can see here 4 case studies of dumbbell specimens with different pore density. In order to describe the associated representative structure elements of the second order, instead of the local stress and strain, global properties will be used, such as, for example, nominal stress, strain, effective stiffness, or the average cube displacement, or anything like this. With this slide, I'd like to conclude my talk. For additively manufactured components, we have a high complexity of microstructure even in thin structures. The population of defects depends largely on the exposure strategy. Due to the number and interaction of defects, conventional design methods reach their limits, at least under the boundary conditions of industrial application. To describe the cyclic behavior of representative structure elements of higher orders, instead of the local stress and strain, global properties will be used, such as nominal stress, strain, effective stiffness of the cube, or an average cube displacement. I would like to thank you all for your kind attention, and will be happy to